So last time we completed the trees, that is normal trees and binary search tree. If you go to the lesson, last lecture, we did completed the tree and then we completed the binary search tree. Today we are going to start a new type, that is 011. It's called binary heaps. Okay, so we will be doing binary heaps. Let's to readme file, and then I'll create one JavaScript file. Okay, so what are binary heaps? These are nothing but a kind of tree. Okay, so these are the kind of tree. Let me put it in the readme. So let's try to understand how the binary heaps work. So in the binary heaps, we have seen the binary search tree which has two children, and each child can have more two childs like this. And the number on the left side should be less than the parent, maybe 5, and the number on the right side should be greater than the parent. Okay, so this is the binary tree. But what happened with the binary heaps? In the binary heaps, there are two types. One is called the max binary heap, and one is called the min binary heap. So let's talk about the max binary heap. In the max binary heap, the number at the top, that is at the parent, is greater than its both child. Okay, so this number, the parent number, is greater than both of the child. So let's say 41 is here, but I can put bigger number here or here. It doesn't matter. Okay, what I mean to say is, let's say I have two child, 39 and 33. So in binary heap, these both child should be less than the parent. In the max binary heap, these both child should be less than the parent. It doesn't matter 33 lies on this side or 33 lies on this side. Side doesn't matter. Okay, so you can put anywhere. You can put here, anything, but both should be less than the parent. Then I can put 18, for example, here, and 27. Both are smaller than 39. I can put 12 here, and let's say this is still yet to be filled. Still we have to fill on the left side. We have filled till this. So let's delete this part. Okay, so this is 12 here. So if you see, 41 has two child, both are smaller. 39 has two child, both are smaller. 33 has now one child will come soon, but both should be smaller than the 33. That's the whole goal. So in max binary heap, parent should always be greater than the child. That is called the max binary heap. Let's talk about the min binary heap. In the min binary heap, the parent should have smaller number. So for example, I put 12, and its child should be greater than the parent. So for example, it can be 27 and 18, for example. Both are greater than 12. Okay, so then I will take here, for example, I'll take 33 greater than 27, and I'll take 39 greater than 27. And here, let me check 41 greater than 18. So the tree is, parent is smaller, both childs are bigger. Then parent is smaller, both child are bigger. Parent is smaller, still we have one child which is bigger than the parent. So this is called the min binary heap. Is that clear? What is the difference between the two binary heap? So if left child is bigger or right child is bigger, it doesn't matter. But both child should be bigger than the parent. Here, left child is smaller and right child should be smaller. But placement doesn't matter. 33 can lie here or 33 can lie here. 39 can come here or 39 can come here. Both are right. So this is a structure of binary heap. We have max here and we have min here. Okay, so that's what we do it. Now, how do we store this value in our data, in our code? So that is important to understand. So when we see this structure, but in the code, we have to put this structure in an array. So this array we have to create, and we have to start with, let's say, 41. So 41 has 0 index because at the root. So 0 index is here. I will put 41. Then 39 is at the 1 number index. So 39 will come here. 33 is at the 2 number index. It will come at the 2 number index. Then let's talk only about this max one. Min is similar to it, so we will not talk about min right now. Delete it. So this is the 2 index. Then this is the 3 number index. So 3 number index, I will put 18 in the array. This is the 4 number index. So 4 number index, I will put 27. And this is 5 number index. I will put 12 in the 5 number index. So the values are stored like in this fashion. That is, each node represents in the array. Is it clear, this part? How we store in the array? Is this part clear? How we store the values? We store the values in the array, and we start with the top 0, then 1, 2, then 3, 4, 5, 6, and go on. Now we have one couple of formulas. With that formula, we can tell what will be the child index of 41. So right now it's a 0 number, so it's very easy to define the child index 1 and 2. But if this goes to 1000 or 1800, 1900, then we use the formula, because then you won't be able to really track who is the child of this 0. So let's try to remember the formula. So you have to remember this formula thoroughly. Because without this formula, we won't be able to do the coding of the binary heaps. So 0 has 2 child, every node has 2 child. So if I want to find the child of 0, I will have the left child and the right child. Let's see what is the formula to get the left child. To get the formula to get the left child is 2 into n plus 1. And to get the right child, the formula is 2 into n plus 2. Sorry. Okay. So let's try to understand now with this formula whether I am able to find the child of this. So if I take the 41 number, it has an index of 0. N is nothing but the index. If I put 0 in this formula, I will get 2 into 0 plus 1, which is equal to, this becomes 0, this is 1. So this will become 1. So left child is at the index of 1. Let's try to find the right child. 2 into 0 because n is nothing but the element which we are considering plus 2, which is equal to 2 into 0 becomes 0, and 0 plus 2 is 2. So that means the index 1 and index 2 are the child of 0. So with this structure, 0 has child of 1 and 2, so we can know that 39 and 33 are the child of 0. Now, based on this formula, can you give me what is the child of 39? Give me the child of 39. Don't look at this diagram. Just follow this formula. Do it in your mind or in your calculator or pen paper. Give me the child of the 1. Correct. Kate has given the correct answer. Ola has given correct answer. It is 3 and 4 because since we are considering 39, that means n is 1. So we can say 2 into 1 plus 1, that is equal to 3. So 3 is the child of this 39. And another is 2 into 1 plus 2, that is 4 as a child. Now, can anyone give me the child of 2? Now give me left and right child of 2. Correct. So it is 5 and 6. 6 is still not, we don't have element yet here, but 2 child will be 5 and 6. Though 6 is not here, but we can expect that the 6 number, if you come, it will become the child of the 2 number. Can anyone give me the child of, let's say we are at the number 1000. So we go on drawing the tree and we are at the number 1000. What is the child of 1000? Can anyone tell me? Correct. It is 2 into 1000 plus 1, that is 2001 and 2002. So even if we have not constructed the tree, but we know the index of 1000, what will be the index of 1000, child index of 1000 and right child index of the 1000. So with these two formula, which is very important, you should remember these two formula to get the child, left child and the right child. This is the formula. So I will put this formula in the Telegram group also. Left child equal to 2n plus 1. Right child equal to 2n plus 2. Now, let's try to understand if I am at the child level, that is if I am at the 4th number level, what will be the index of the parent? So with the formula, we'll try to extract the parent index. These two formulas are for the child index. But what if I am at the number 12? What would be the parent of this 12? We will write a formula for that also. With this small image, it is easy to calculate. It is easy to see which is the parent of this one. But if the tree grows large and we have millions of data, then we should know with the formula who will be the parent of this one. Okay, so that's what we will try to do now. So the formula to extract the parent is this one. So we need to use the floor. Everyone knows what is floor is. We need to use the floor, and we have to say n minus 1 divided by 2. So for example, if I'm at the number 39, that is index is 1. So n is 1. Parent, the top root 1 is always 0. So this is the exception. You don't worry if it's a 0, that means this is the parent. There's no parent above if it's a 0. But let's try to get the parent of 1 and 2 in this formula. So I will put 1 instead of n. 1 minus 1, 0, divided by 2. So 0 by 2 is 0. That means the parent of 1 is 0. Let's try to find the parent of this one. 2 minus 1, n minus 1, that is 2 minus 1 divided by 2. 2 minus 1 is 1. 1 upon 2 is 0.5. If I take floor of 0.5, floor means it should be at the lowest level, so it is a 0. That means the parent of 2 is 0. Let's try to find the parent of this 3 number. Into this. So instead of n, I will put the 3 number. So I'll say 3 minus 1 divided by 2. 3 minus 1 is 2. 2 divided by 2 is 1. So the parent of 3 is 1. Now you try to find the parent of 4 number using this formula without looking at this tree. Use this formula, try to put the values in this formula, try to see what is the parent of 4 number. Correct. The parent of 4 number is 1. Try to find the parent of 5 number using the formula. 2. Correct. Try to find the parent of 500. We are at the 500. What is the parent of 500? 2.9. Let's calculate. 500 minus 1, it becomes 499. 499 divided by 2, it is 249. So we have to take the floor. So the parent of 100 is 249. Correct. So Kate has given correct answer. So this way we can go from top to bottom, or we can go from bottom to top. Okay, so this one was the understanding of the binary heaps, how we the child, how we calculate parent. Let me write down the formula of parent in the reactor diagram. And floor of n minus 1 divided by 2. Okay, now how many are we here? Okay, so now we'll play a small game using the binary heap. Oh, sorry. So right now, right now I will not consider this value part. Okay, I will not consider value part, but we will only calculate the index to see who is the parent and child. Okay, the value we will do in the coding how to move the values based on this logic. So let me see who is what. Let's say I give a number to Anand. Okay. So B number is Ashok, C number is Kate, D, everyone remember your own number. Ole, Welsh. Okay, E number is SY. Okay, so you should remember your number. I will start with a number and I will take $1 from a number. So a number is now having -$1 because I took money from him, that is $1. So a number should remember how much money he has now. Okay, we will go on by, we will go in the tree and we will give some money to everyone. Okay, using this logic, it is 0 number index. I will draw this array. Okay, a number at 0 number, we have a. He gave me $1, so he has -1 in his pocket. So no, sorry, I have cough. Last week also I was sick. This week I am also sick, but I am taking class this week. Okay, now A has 2 child. First child is B number and second child is C number. B number will give me $1. So B number has now -1. C number will also give me $1. C number is having -1. Okay, now this is the index. Now what I will do, I will take this $1 and take this $1, I will give it to A number. A number will get $2 now. Now A number, you should remember what money you have total. Okay. So what is your earnings? Now, yeah, A number has $1. I will not put everyone's money here. I am just beginning, so I am putting it as soon as we'll go. We'll play only 5 minutes, not very large game. Only 5 minutes we'll play this game and see who has what money in it. Then B has 2 child now. Now it's a D and E. He will give me $1 and he will give me $1. So D is now having -1. E is also having -1. I will give this $2 to B. So now B is having $2 plus. He invested -1 initially. Now he has $2. So what is the final amount he has? $1 because he put his own money and he got his own money. Yeah. Now C got 2 child. Now here again we will go with A because we don't have many people. So A will come, he will put $1 and B will put, he will get $1. Both these dollar will go to C. So C will get $2. So C, you should remember you have $1 now. So after this, A and B. Then comes again child of D. Child of D, I will take C and I'll take D. Though it is D same, but this is the hypothetical. It's fine if we have child as child same. Okay, in real world, we have this number as we said. Okay, so it will be $1 here and $1 which will go to D. So D will get $2 now. Now E will get two child. That is one of the E and one again A. So $1 this one will give, $1 this one will give. So this will be -1. Okay. And this both will go to E. So E will get 2. Now I will not update this. You have to update your money. Okay, as soon as I flow. I will put one more round here and then we are done. We'll see who earns what. After A, we have B and C. They will give $1. These $2 will go to 2 here, A. And then B has D and E. Both will earn $1. So $2 will go to B. Then C has child of A and B. So C will get $2. Though I did not calculate -1 here, where you put -1, so you have to take care of that also. D will get child of C and D. So both money will get to D. So you should calculate as per. You should also subtract this one when you give money. You should plus it when you receive money. E will get child of E and A. A will get child of B. So one go here. A will get child of B and C. One here. B will get child of D and E. One goes here and goes to B. C will get A and B. And this one will get C and D. And last one E will get again child of E and A. So after this, we are done. We are done the game. So have you calculated the money? Each one. So everyone should write their own money. So you can also do it here that when you give the money, just do -1. When you receive the money, you +1. So with that, is it possible? Okay, Anand got $2. What about others? Have you calculated? But even if you go $2 or $1, as soon as this chain will grow, you will also get more money. Okay, this is the fun game. Nothing to really related to the programming. Okay, this is just a fun game. You calculate your money, and tomorrow you will get that in your bank. Okay, this is not the real pyramid selling. Pyramid selling is something when you. This is not the pyramid. It's a pyramid, but it's not a pyramid selling, because in the pyramid you have to find your child yourself. Okay, if you can have 10 child also, you will get the money from all 10. But here, you don't have to calculate the 10 child. It's automatic with the formula. Okay, so pyramid selling is illegal in everywhere. This one, no one has adopted this logic, so we don't know if it is legal or illegal. But with the pyramid chain, that is illegal all over the world. With this one, we are just playing the game. Really, in real, nobody has implemented this one in the real world. So we don't know if it's illegal or illegal. Okay, let's start to code now. Let's go to the coding. Okay, so as I showed you, let's start to draw a simple diagram again. To explain the max heap, this is the top one. We'll not draw big diagram. Okay, so here it's the 41, and then I have 39, 33, 18, 27, 12. Okay, so this is the tree which we will use in our example. Okay, so now we will create a class or function called as max binary heap. So in this, I will create first one called as dummy or variable called as values. It is an array where all the values will be stored, and based on the formula, we will go child or parent in some cases. So here we will write first function, that is the insert, and then another function we will write is remove. It's kind of remove, but remove special here, which I will explain you in a minute, or maybe next time. I don't know if we reach this today or not. So these two functions we have to understand in the max binary heap. Okay, let's try to go with the insert part first. Okay, before I go, just write down the structure and then I will go further. Okay, so let's try to create a variable heap, and this one will be new max binary heap, and then I will call the heap dot insert. I will put some number here what I want to insert. Let's take 41 now. So how to insert the values? Let's try to understand the structure of how to insert it. So when nothing is in the root, we will just add in the root, for example, 41. But then Then we add another number. And then here, let's say if I put 39, then I have to restructure this tree so that it should be proper max binary heap. So for example, let's say if I create in the top 39 first, and then I push 41. So as soon as I push 41, I will put it first in the end. I will put 41 at the end of this one. So 39 is here. Initially, I will put 41 in the end. Then I will write the code so that it should go to the proper max binary heap. So I will compare this 41 with the parent. And if the parent is smaller, I will swap it. So the new value will be 41 will come here and 39 will come here. So what we did, first we put 41 and then we compare it with parent. If parent is smaller, then we swap the parent with the current element, and then we get the proper tree. Remember, parent should always be greater than left and right child. If I put 55 here, let's say if I put 55 here, so initially what I will do, I will put this 55. So this is the tree, for example, 41 and 39. I put the 55 in the end. 55 is not at the correct spot, but as soon as someone try to put 55, I will put in the end of the array, and then based on the logic that 55 should be greater than the this 41, so 55 should move to the parent. So I will check the parent of 55, which is 41, and I will see the parent is smaller, so I will replace 55 with the 41. So 41 will go here, and 55 will go here. So that will happen like this. Okay, so the new tree will become 55, 39, and 41. Let's say if I want to add new element, for example, 100. So first I will put it at the end, and then I will check 100 with the parent, 39. So 39 is smaller, so we will swap these two numbers. So 100 will come here, come here. Then again I will check 100 with the parent. Still 55 smaller, so 55 will go here and 100 will go here. And then this is the proper max tree. So what we are doing? First we are adding it at the end, and then we are comparing with the parent and go on doing parent till we reach the root, and after root we are done. Okay, so that's what we will be doing it in the code level. Okay, let's start now. So as soon as you put some value in the insert value, I will just put value in this values one. So first step is push the value in this values. So first step is push the new value at the end of the array. So how we will do? I will say this dot values dot push, and I would pass the wall. And after I push, I will just try to see what is the values is here. Okay, now if I try to insert 41, then let's insert 39. Then let's insert heap dot insert 55. Okay, let's check what happens here. So initially we put 41, then we put 39 at the end, then we put 55. But 55 is not at the correct spot. So whenever we put something, then we have to go through our logic or the loop to check whether the new value is at the correct spot or not. As per maximum binary heap, the 55 should come here, but it is still at the end. So after we insert it, we will write some code here so that 55 should go to the correct place. Okay. So before I write the logic here, I will like the step 2, write a logic to move the new value to correct spot. Okay, that is what we will do here. So before I go further, just write down these 3 lines in the insert, and then we will write this logic. Okay, now let's try to do the logic here to move the value to the correct spot. So generally, if we have only one element in the values, because we are pushing it, that means if we now have only one value in the values, then we don't need this logic. Okay, so I can say if this dot values dot length equal to 1, that means there is only one value in the values 1. That means this is entered in the root. Then we don't need to bubble up. We don't need to push it to the top level. So we'll just return it. Okay, we will not do anything. Okay, so we will not do anything if it is 1. That means we were having empty values, and now we got only one value entered in the values. That means the array has no previous value. We added only one value, and so the value length is 1. So we don't need to go up level. We don't need it. Okay, we need only when we have more than one value. So here I can write, if we have only one value in values variable, that means it is root node, and we don't need any logic to process it. Logic is needed when we have more than one element. Otherwise, we don't need the logic. Process the element. Okay. Is this clear? This part is clear? Write on this part. Okay, now let's clear it. Now we have 0 element. I added, for example, 39. For example. Okay, so we don't need any logic because this is only one element, and in our array, it got 39 here, 0 number. Now let's try to add a new element that is called 41. So first step is put this 41 at the end. So I'll put this 41 at the end, which we already are doing it now. This one, this line, we are adding it in the end. Now we have to write the logic that it should be at proper place. So which element should be at the proper place? The new one which we have added it. So let's take the index of the new one. What is the index of the new one? It is 1. But how we will get using the code? We will say, I will show you in the code I will write down. So get the index of the new element added. So I will say let index equal to, since this is the last element in the array, to get the last element in the array, what we write? Can anyone tell me how to get the last element in the array? I want the index of the last element. What will be the last element of the array? 1. But how will I write in the code? Array.length minus 1. Correct. So this length minus 1 is the index of the last element. So I will say this dot values dot length minus 1. This is the index of the last element of the array. So we have taken the index of the new element added, and I will also take the get the value of the last element. Though it is this wall, but I will again take it here for the purpose of calculation, but I can also use this wall if I want. But let's try to put it in a variable, and if I want I can take wall also. Both are correct. Get the value of the last element added. This is the index, and I will take the value. Though I can take value directly here, but let's take with the help of formula. So I say constant element is equal to this dot values of index. Because this is the last index, the values of this index will be the last element, so I put it in the element. Let me do the console. New element added is element. Console.log new elements index is idx. Okay. So we will console these two to see what is the index and what is the element. Okay. So let's try to run and see. Let's put this as a 39, and then I'll put 41. I'll remove 55 for now. So you will see initially 39 is already added. We don't process if it is the first element, but we are processing when it is the second element. So the new element is 41 and the element index is 1 as per this diagram. Index is 1. Okay, now what? Let's see what we have to do now. Okay, now as I told you, we have to go to parent and parent and parent. If it is one level like here, then we will only go to one level parent. But when the new element come here, after we fill here and then new element comes here, then to go to parent and parent all. Since we have to go to parent, that means this tree can grow very large, up to 1 million, 2 million. So we have to go parent. So that means we have to write a loop. So it will go to parent till it reaches this spot. Okay, so let's try to write down this loop. Now, since we need to go to parent, parents, 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 parent, till we are at right spot, so we need the loop. So I will put while. I will put the condition in a minute. Then let's try to put in the while first. Okay. So in each while loop, I want to see what is the value look like. Okay, so let's try to console something here. Console.log values before loop is the. I will put JSON.stringify this dot values. And I will also put after the loop, means at the end, to see what is the values at the end. Here I'll write some code. So whenever we get this element, we have to compare it with the parent. Okay, as I explained you, we have to compare it with the parent. This is the parent, this is the child added. Since we have to compare with the parent, I will take the parent index equal to something will come. Right now, let's make blah 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 blah. And I will also get the value of the parent. So I will say parent value equal to, because I need to compare the parent value with this element, whether which one is greater, which one is smaller. So parent value will be nothing but this dot values of parent index. So this index will come here. So let's say in this example, this one is index of 1, this is the 0. So the parent index is 0 and the parent value is 39. So we need these two things, this one and this one. That's why I put parent index and the parent value. So as you know, with the formula which I gave in the few minutes back, the formula, let's write down the formula here. If I want to find the parent's formula is parent is equal to math.floor n minus 1 divided by 2. So this is the formula which we have to use it. So here I want to find the parent of the current element, that is this idx. So what I will do, I will write down math.floor, and here I will say idx minus 1 divided by 2. Okay, so we are at this index, and in our diagram, this index is 1. So we will do 1 minus 1, that is 0, 0 upon 2, it is 0. So parent index will be 0, that is this one, and the parent value will be values of 0, that is 39. Okay, so this one will be 0 in this case, and this one will be 39 in our example. Let's write down 2 here, for example, now. So we have to go this looping only if this index is greater than 0. Once index reaches the 0 or it is less than 0, we don't have to go inside it, because if it is 0, that means we are at the root level. We don't want to find the parent of the root level. So instead of true, I say index should be greater than 0. So if index is greater than 0, then only we will process it. If index is 0, that means we are at the root level. We don't have any parent of that. This processing will only done for the parent. To find the parent, compare it, swap it. But if index is 0, we don't need to find a parent. So this will not work in the root case. Okay, so we found the parent index, that is 0. We found the parent value, that is 39. Now what? Now we have to compare this element with this 39. This element in this case is 41. I have to compare this 41 with 39. And if this element is bigger than this parent, then we have to swap. So this one, if it is bigger than this one, then we have to swap. Okay, so let's write on that thing. Here, I will write down the reverse case. I will say if element is less than the parent, less or equal to parent. So this reverse case means if element is less than this parent. So let's take another example. I put 41 here and I put 39. So I'll check this is the element, this is the parent. I will check 39 is less than parent. 39 is less than parent. Then we don't need to swap. We don't need to swap. So then in that case, we have to come out of the loop. Come out of the loop. Loop exit. Because we only want to go to parent if parent is smaller than the current element. If parent is bigger, that means we are at the correct spot. So what we will do, if element is smaller than the parent, then we don't need the logic to swap. Here the logic will come to swap. But if element is smaller than the parent, then that means element is at correct spot. We don't need logic to swap. So here I will say, I will break. I will come out of the while loop. And we are out of the while loop. Okay. If element is less than or equal to parent value, not the parent, sorry, parent value. Okay, so this is the parent value. We are checking the values, not the index. So if element is less than the parent, that means we are at the correct spot. If element is bigger, then only we have to put it at the proper place of the tree. Is that clear? This part clear? Any questions on this part? We find the parent value. And we check if element is less than the parent, then we come out of the loop, because if element is smaller, we know that parent should be bigger. If parent is smaller, then we swap. But if parent is already bigger, then we don't need to do anything. Okay, let's do now again more. Now we have to write the logic to swap. But if element is bigger than the parent value, for example, in our example, let me show you example. This case, 41 is greater than 39. So in this case, we will compare 41 with the 39. Since 41 is greater, so we have to swap. We have to swap these two values. So let's do that swap. I will say this dot values. So I will put something in the parent index. Something will come here, and I will put something in the index. I will put it something here. So this is the index. I is the index IDX, and this is the parent index. Parent index. Since we need to swap, that means parent index should get this 41, and index should get this 39 value. Okay, so that's what we have to do. So I'll say the parent index should get this one, 41. 41 is nothing but the element in our case, in element, variable element. 41 is nothing but the element. So this element will go to parent index. So the parent index will get the child, that is element, and index will get the parent value. We have to swap. We have to do parent index. We have to put 41 in the parent index and to put 39 in the index part. 39 is nothing but a parent value, and 41 is nothing but this element. So 41 will go to parent index and 39 will go to index. So we are swapping. This is the swapping logic. And once we swapped it, this index part from 1 will move to the 0 number, because now we have to take 0 number and compare with the parent. So here it is no parent, but we need to change the index to the parent because we need to compare with the parent. So that means we need to change index to parent. So that means index will be equal to parent index. And index will become parent index, then while loop will continue. If x is greater than 0, then again we find new parent value, compare with the current element, and if element is bigger, then we write down this logic to swap again, and we change the index again to its parent. Okay, that's what we will be doing it. Let's try to run this and see how it looks like. Okay, so first 39 will go itself. We don't do the looping. Then the new element added is 41. Its index is 1. Values before the loop. Before loop, we have 39 and 41. And then we check if 41, what is the parent of 41? 39. We check 41 is greater than 39. Yes. Then we swap. And after it, we get these values like this. So I will say heap dot values, it's 41 and 39. Let's try to insert another one, 55. Okay, so when I add 55, new element is 55, index is 2. Before loop we have 55. We check compare 55 with its parent using the formula. So 55 and 41. 55 is bigger, so we swap. And 55 becomes here and 41 becomes here. Let's try to add another one. 33. Since 33 is smaller than everything, so 33, as soon as I insert 33, it will be at the last level and it does not need to go up. So it is saying 55, 39, 41, 33. Since 33 is the smaller than all, it will not travel to up. And we get only before loop because we break it. We break it here only. We break it here. If element is smaller, then the parent value, we don't even go to swapping logic. Let's try to add another one. Maybe 100. So first 100's parent is this 39. So 100 is swapped with the 39. And then 100 again goes compared to 55. So 100 is now compared to 55. So 100 goes to the top and all other goes below. Let's try to add 1000 now. It should be going. So initially 1000 is added at the end. Then it finds a parent that is 41. It goes here. Then again it finds the parent and it changes position here. So that is how we are adding it. Before I finish this part, just write down this while logic. Maybe you have written something, so finish the while logic. And try to understand each line. And if you don't understand any line, I will explain you that. But then also you can watch video again to understand what's happening. So I'll give you 2 minutes to finish this logic. Yeah, magic happens here. then we swap the elements here. Okay, try to run this in your console. And let me put more console and then I'll run again one time. Parent index is parent index, parent value is parent value. I'll put some console, more console. Here I'll say element is smaller than parent value. So exiting. Here I'll put console.log since element is bigger than parent value. So swapping both. Okay, so let's write on this. Let's start this one. Okay, so this is my heap. Now I will try to insert. First element heap dot insert. I will put 39. First element. Nothing happens because it is a root one. It goes into the root. If I want to see heap dot values, it has only one value now, 39. Now let's try to insert again. 41. Since 41 is bigger, so they will swap it. So new element is 41. Index is 1. Values before loop 39, 41. Parent index is 0. So parent index of 41 is based on the formula is 0, that is 39. Since the element 41 is bigger than the parent 39, so swapping both. So we are swapping it here. Let's try to put smaller one now, 33. So new element is 33, new element index is 2, list before this 33 is at the end, parent is 0, parent of 33 is 0, that is 41. Element 33 is smaller than the parent. So exiting, we don't need anything to do. If we want to see the values now, it is like 41, 39, 33. Now let's try to add 55. So edit 55, its index 3, parent is 1, that is 39. Since element 55 is bigger, so swapping both, so 55 will go here, 39 will come here. Then from 55 we'll compare it with the 41. Parent of 55 is 41. Parent is 0, parent value is 41. So element 55 is bigger than the parent 41, so swapping both. So 55 will go here and 41 will stop it here. This is the final one. Okay, so that's all about the insert part. And another important thing which you have to do is the remove part, which we will do next time. So this is the remove part, which we will do next time. But as a homework, I will give you one homework. We created this max binary heap where we check parent should be greater than the child. Try to make same thing with the min binary heap. Min binary heap will be parent will be smaller than the child. So whatever you will add, you have to change the logic so that the parent should be always smaller and the new element which is added is always bigger. Child should be bigger. So only few things you have to change it. I will not tell you what things to be changed. This you have to take. I will put it in the React library group, in a React Telegram group also. So you have to take this example and try to do the min binary heap. I will not do min binary heap. I want you to do and give me the answer for the min binary heap. Min binary heap means parent is always smaller than the child. So there will be few logic which you have to add here in this part. You have to reverse the thing that parent should be greater and element should be smaller. Okay, so here you have to change it, otherwise rest of the logic will remain same. And you have to try it with the min, whether it's working correctly or not. Is that clear? That is the homework for the next week. That's all for today.